right now, there are nearly 130 million pieces of jagged metal, frozen coolant, and just like dead satellites flying above your head at terrifying speeds.
Yeah, and we're looking at less than 3 days on a literal sea or ash clock to prevent this catastrophic orbital pileup.
Which is just wild. But our best defense against this, invisible garbage dump, it isn't some high-tech spaceship with lasers or giant nets.
No, it's actually the sun.
Exactly. So today, our mission on this deep dive is to explore exactly how that works. We're unpacking a really fascinating piece of research that was published on May 15th, 2026 in the journal Frontiers in Astronomy and Space Sciences.
Right, and it's a dynamic that sounds, completely like science fiction.
Yeah.
But it is actively dictating the future of our planet's immediate cosmic neighborhood.
It really is. So where do we even start with this?
Well, it fundamentally changes how we understand the environment just outside our atmosphere. Because, when most people picture space, they imagine this dark, static, totally empty void.
Right, like a complete vacuum.
Exactly. But to really grasp the mechanics here, you have to picture a very specific visual from the research. Imagine the Earth as seen from a distance. You see the curvature of the planet, and it's shrouded in this incredibly delicate, glowing layer of clouds and atmospheric gases.
Oh, wow. Okay.
And right over the horizon, the sun is shining brilliantly. It's casting this intense radiation right across the vacuum. That visual perfectly captures the two main characters of our deep dive today, solar radiation and our planet's fragile, gaseous envelope.
Okay, let's unpack this, because when we talk about cleaning up space, a very specific analogy comes to mind.
Hey, let's hear it.
Imagine this massive highway in the sky, and it is completely filled with speeding, driverless cars that are totally out of control.
That is a terrifying thought, but yeah.
Right, and we can't possibly afford to send a fleet of, high-tech tow trucks up there to catch every single runaway vehicle. I mean, it would bankrupt the global economy.
Oh, absolutely.
But instead of sending tow trucks, imagine if the weather changed and the atmosphere itself could occasionally act like a giant sponge. It just reaches up, creates drag, slows those cars down, and pulls them safely out of the lane so they just burn up upon reentry.
That highway analogy perfectly isolates the physics we are dealing with here. The sponge is the physical friction of Earth's atmosphere. And the trigger that makes the sponge reach up, well, that's the sun.
Which is so cool.
But before we dive into the mechanics of that solar trigger, we really need to understand the sheer, overwhelming scale of this orbital mess. The numbers we are looking at are not just large.
They're terrifying.
They represent an immediate compounding crisis.
Yeah, I mean, we are talking about 130 million fragments currently circling the planet. And these aren't just like empty soda cans floating lazily by.
Not at all.
These are fragments of orbital scrap metal moving at thousands of miles per hour, completely uncontrolled. I read that a fleck of paint moving at those velocities can strike with the force of a bullet.
It absolutely can. And an entire dead satellite, tumbling blindly, is essentially a localized weapon of mass destruction for anything in its path.
So the statistical probability of a collision is just this constant looming threat.
Exactly. And this is where that sea or ash clock concept comes into play. A warning of just 2.8 days to avoid a worst-case scenario that isn't some vague, distant possibility.
It's right around the corner.
Right. It means the orbital trajectories of these uncontrolled fragments are actively intersecting with critical infrastructure.
And a single collision in low Earth orbit doesn't just destroy two objects, right?
No, it creates thousands of new, smaller fragments, which then scatter and instantly increase the probability of further collisions. It's this terrifying cascade effect.
So understanding how this debris naturally behaves, how it decays, is absolutely critical. Otherwise, entire orbital lanes just become completely unusable.
Right.
But you might be wondering, and I'm asking this for you, the listener, if space is a vacuum, how does this atmospheric sponge ever grab the cars?
That is the big question.
Because we are taught from a very young age that space is a complete void. There's no air, there's no wind, there's no friction.
Right.
So if there is zero resistance, shouldn't a dead satellite just stay up there, coasting perfectly in its orbit until the end of time?
Clearing up that misconception is really step one in understanding orbital mechanics. The term space is, incredibly broad.
Okay.
The specific region we're discussing, low Earth orbit, where the vast majority of this 130 million piece debris field lives, it is not a perfect vacuum.
Wait, really? It's not empty?
No, it's a transition zone. There's actually a residual atmosphere up there. It's an incredibly sparse, virtually undetectable layer of gas.
Huh.
I mean, obviously you can't breathe it and it wouldn't feel like a breeze on your face, but on a molecular level, it is physically there.
So it's not a complete pristine void. There are still stray molecules floating around, forming this extremely thin envelope.
Precisely. Gas molecules are scattered throughout this entire orbital zone, and this thin gaseous envelope acts as a persistent, unavoidable brake pedal.
Okay, a brake pedal.
Yeah, it is constantly creating drag on every single object moving through it. When a piece of debris traveling at orbital velocities strikes one of those sparse gas molecules, a microscopic transfer of kinetic energy occurs.
So it bumps into it and slows down.
Basically, yeah.
Yeah.
The debris loses an infinitesimally small amount of forward momentum. Over days, months, and years, that constant minor friction degrades the object's orbit.
Wow.
It begins to decay, spiraling closer and closer to Earth until it finally hits the thicker, lower parts of the atmosphere and just incinerates.
Okay, so the residual atmosphere is the brake pedal naturally slowing down the space junk. But if that molecular friction is so microscopic and so agonizingly slow, how does the sun suddenly speed up the process?
That's the cool part.
Like, what is actively pushing down on that brake pedal to accelerate the cleanup?
Well, the mechanism comes down to the direct interaction between solar energy and our upper atmosphere. You have to remember, the sun is not a static light bulb.
Right, it's a massive, violent star.
Exactly. It's a roiling, dynamic star. When the sun becomes active and agitated, it releases massive amounts of energy, solar flares, coronal mass ejections, highly intense ultraviolet radiation.
And all that energy has to go somewhere.
Right. That wave of extrasolar energy travels across the solar system and slams directly into Earth's atmospheric envelope.
And when gases absorb that kind of intense thermal energy, they become highly agitated, right? They heat up and they expand.
Yes. This triggers what researchers call the dilation effect. The gases in our upper atmosphere become incredibly energetic. They can't be contained in their usual volume, so the entire atmosphere physically dilates.
It swells up.
It swells outward, stretching much further into space and reaching significantly higher altitudes than it normally would during, a calm solar period.
Okay, I want to make this tactile for a second. Imagine you're running on a treadmill in a totally empty room. You're sprinting. There is zero air resistance, and your pace is effortless.
Okay, I'm picturing it.
Now, imagine someone suddenly opens a valve and floods that room with waist-deep water. You haven't changed your stride, but the resistance has dramatically, violently increased.
That's exactly what happens in orbit.
Right, because the Earth's atmosphere has dilated outward. This space debris, which was previously coasting through a relatively clear, sparse area of the vacuum, suddenly finds itself plowing through much denser gas.
Yep. It experiences far more drag, loses momentum rapidly, and its downward spiral toward the incinerator just totally accelerates.
That is wild.
What's truly fascinating here is the sheer physical causality of it all. We are observing a direct mechanical link between the volatile mood of a star 93 million miles away and the precise physical friction experienced by man-made objects just a few hundred miles above our heads.
It's like the star throws a tantrum, our planet's gaseous envelope puffs out in defense, and millions of pieces of orbital garbage get dragged out of the sky.
Exactly. The theoretical physics make complete sense, but, proving it is an entirely different challenge.
I can imagine. You can't just put a piece of space junk in a vacuum chamber, turn a giant heat lamp on it, and simulate decades of orbital decay.
No, you definitely can't. You have to observe it in the wild.
And observation on this scale requires a level of patience and meticulous data collection that is rare even in astrophysics.
It really is.
Yeah.
To move this from a logical theory to an undeniable scientific fact, the researchers had to conduct this massive 36-year-long observational study.
36 years. Wow.
Yeah. They tracked 17 specific pieces of space debris. And these weren't freshly launched fragments either.
Right. These were objects put into orbit way back in the 1960s. They spent nearly 4 decades watching these specific pieces of ancient scrap metal slowly circle the globe.
And that 36-year time frame, it isn't just a random number drawn out of a hat.
No,
that perfectly covers exactly 3 11-year solar cycles. They wanted to watch the sun's entire mood swing from completely calm to entirely chaotic 3 separate times.
Okay, that is the genius of the methodology right there. By observing across 3 complete solar cycles, the research team gained a comprehensive long-term look at the extremes of solar weather.
Exactly. They could document the baseline orbital decay of these 17 objects when the sun was at its absolute quietest, and then compare it to the sudden spikes in drag when the sun reached its maximum agitation.
Which eliminates short-term anomalies and reveals the undeniable long-term pattern.
Yes. But, looking at the debris is only half the equation. To prove the atmosphere was expanding because of the sun, they needed a pristine record of the sun's behavior over those exact same 36 years.
Right, they had to cross-reference it.
Exactly. So they took their meticulous tracking data for the 17 objects and crossed it with historical solar activity records meticulously kept by the German Research Center for Geosciences.
Layering those two massive data sets, that's where the undeniable correlations emerge, right?
Oh, absolutely. They placed the precise daily altitude and velocity of the 1960s debris directly over the exact measurements of solar radiation and flare activity from the Geosciences Center.
That's a lot of data.
They weren't just looking for a general trend. They were looking for precise, synchronous reactions over almost 13,000 days of observation.
So they have this incredible 36-year stakeout comparing the falling altitude of Cold War-era space junk against the German Geosciences solar records. What actually happens in the data when the sun throws one of these 11-year tantrums?
Well, the baseline finding immediately validated the core theory. The data showed a direct, irrefutable relationship. When the solar records indicated high activity, the atmospheric density at the debris altitude predictably increased.
And the resulting extra resistance ruined the object's stable orbits and precipitated a faster fall toward Earth.
Precisely.
But here's where it gets really interesting, though. Because finding out that more sun equals more drag, that's a solid confirmation, but it might seem a bit intuitive to an astrophysicist. However, lead researcher Aisha Ashraf and her team uncovered a brand new discovery hidden deep within those 3 decades of data. They didn't just find a gradual linear effect.
No, they didn't.
They didn't find a simple 1-to-1 ratio where a 5% increase in solar flares equals a 5% increase in drag. They found a rigid mathematical threshold.
And the discovery of this specific threshold fundamentally alters our models of orbital mechanics.
Yeah.
Ashraf noted this startling reality beyond a certain specific level of solar activity. The loss of altitude for these objects doesn't just increase at a steady pace.
It accelerates exponentially.
Yes. It is as if the sun decides it has finally had enough of the mess in our orbit, and instead of just turning the vacuum cleaner on, it instantly cranks the dial from the low setting straight to maximum overdrive.
Wow. Maximum overdrive.
The drag becomes violently more effective once that threshold is crossed. The atmospheric expansion at that peak level becomes so significant, so dense, that the cleanup process shifts into an entirely different gear.
So the altitude loss happens significantly faster than previous linear models would have ever predicted.
Much faster. The sheer volume of debris pulled down during these overdrive periods is staggering.
Which sounds incredibly, incredibly optimistic. I mean, if we have 130 million pieces of dangerous shrapnel threatening our CR ash clock, and the sun periodically acts as an overdrive vacuum cleaner to wipe the slate clean, that feels like a massive win for the future of spaceflight.
It does sound like a win.
Oy.
But physics rarely hands out free favors without a catch.
And the catch here is severe, isn't it? It impacts the core of our modern global infrastructure.
It really does.
Because I have to push back on this idealized image of the solar janitor. If that atmospheric sponge is swelling miles out into space, grabbing onto useless 1960s junk and dragging it down into the incinerator, well, it does not discriminate.
Not at all.
It doesn't know the difference between a dead piece of scrap metal and a brand new multi-million-dollar communications satellite that we desperately need to stay exactly where it is.
That deduction hits on the exact engineering nightmare the space industry is facing right now. The atmosphere is entirely blind.
Right.
During these peaks in solar activity, when the threshold is crossed and the gaseous envelope dilates into that overdrive state, active operational satellites suffer from the exact same exponential drag as the dead debris.
So all of our vital infrastructure, the satellites powering global GPS, tracking hurricanes, managing financial transactions, they are suddenly swimming in that waist-deep water too.
Exactly. They're hitting that wall of dense gas. And unlike the dead debris, which we want to fall, those active satellites cannot simply surrender to the drag.
Because their survival depends on holding a very precise altitude and trajectory.
Right. To avoid being dragged into the thicker atmosphere and burning up, these operational satellites must physically fight back against the expanded environment.
So ground control has to constantly command them to perform more frequent orbital corrections.
Yes, meaning they have to fire their onboard thrusters just to push themselves back up into their proper lane on the highway.
They have to actively thrust against the density of the atmosphere. And every single time they fire those thrusters, they are burning through their onboard fuel.
And this is where Aisha Ashraf issues a very stark warning about the long-term consequences of this battle. Every satellite is launched with a finite, strictly limited quantity of propellant.
Because there are no gas stations in the low Earth orbit.
Exactly, 0 gas stations.
Huh.
Once a satellite runs out of fuel, it is effectively dead. It can't correct its orbit, it can't orient its solar panels, and it becomes just another uncontrolled piece of the 130 million fragment debris field.
So the harder the sun pushes the atmosphere out, the faster our satellites have to bleed their fuel just to tread water.
It drains the absolute lifeblood they need to survive their planned mission durations. This creates a massive, multi-million-dollar headache.
Especially for new missions, right?
Oh, particularly for new missions that happen to be scheduled for launch right as the 11-year cycle approaches a solar maximum.
Because if you place a brand new satellite into orbit right as the sun crosses that threshold of extreme activity, that incredibly expensive machine is immediately going to start rapidly depleting its fuel reserves just to maintain its starting position against the overdrive drag.
Yep. If we connect this to the bigger picture, the entire paradigm of planning space missions shifts. It requires an intimate, highly accurate understanding of a decade-long solar weather forecast.
You aren't merely calculating the orbital physics and the payload weight for the launch anymore.
No, you are essentially betting against the temper of the sun for the next 11 years. Mission planners have to calculate exactly when that threshold is going to be crossed.
And they have to pack enough heavy, expensive fuel to ensure the satellite can survive the sun's aggressive cleanup efforts without running dry halfway through its lifespan.
It is this incredibly delicate, invisible war going on hundreds of miles above our heads.
Let's bring all of these moving parts together because it is a profound system to wrap your mind around. On one side of the ledger, we have a terrifying reality. Nearly 130 million fragments of debris governed by a Cher-Ash clock, threatening to trigger a worst-case scenario that could lock us out of orbit entirely.
Right.
We have a residual atmosphere, a sparse layer of molecules that acts as a natural brake pedal, and we have our star operating on these massive 11-year cycles.
When the sun throws a tantrum, it heats that atmosphere, causing it to dilate and expand outward.
Which triggers an overdrive cleanup effect, dragging dangerous junk out of the sky exponentially faster once a specific solar threshold is breached.
Exactly.
But on the other side of the ledger, we have the desperate, constant battle to keep our active satellites alive in that exact same expanding sponge. Every time you pull up directions on your phone, check a global weather radar, or rely on international communications, those machines in the sky are silently fighting for their lives.
They are firing thrusters, burning precious, irreplaceable fuel, and fighting an invisible solar tide just to stay in their lanes.
So what does this all mean? We have identified the massive scale of the debris problem, the incredibly elegant solar mechanism that naturally cleans it up, and the severe complication it causes for our active technology.
Well, it leaves us with a profound paradox and a somewhat unsettling thought regarding the future. We know we rely heavily on these periods of maximum solar activity to act as our cosmic janitor.
Right, the overdrive drag is the only viable mechanism keeping that debris field from completely overwhelming our orbital lanes.
But what if the sun's highly predictable 11-year cycles suddenly change? Historically, stars can enter what is known as a prolonged solar minimum, a period where solar activity remains incredibly calm, incredibly quiet.
And not just for a few years, but for decades at a time.
Exactly. If we are entirely reliant on the sun's violent tantrums to expand the atmosphere and clean our orbit, what happens if the sun simply goes to sleep?
Oh, wow.
Without that crucial overdrive gear expanding the atmosphere and pulling the trash down, do we rapidly lose the battle against the Cher-Ash clock? If the cosmic janitor takes a 30-year vacation, we might just find ourselves completely drowning in our own orbital debris.
That is a staggering implication to consider. The very calm we might hope for to save our satellite's fuel could actually be the exact thing that allows the debris field to multiply beyond control. Well, thank you for joining us on this deep dive. We hope this exploration of the invisible forces battling above our atmosphere gives you an entirely new perspective the next time you feel the heat of the sun on your face. Take care and keep looking up.